All right, let's turn our attention now to section 14.3. We're going to talk about change of variables into polar coordinates. Now, we've seen in previous courses that polar coordinates can be a useful alternative representation to a region. We can deal with things in rectangular coordinates, but oftentimes if the object we're dealing with is curved, if it's part of a parabola or a sphere or something along those lines, we often have an easier time dealing with it if it is expressed in polar coordinates. But now, how do we do that? Well, let's consider something all the way back from trigonometry. Let's remind ourselves of the area of a sector. A sector is like a slice of pizza, yeah? Pie wedge. It's a wedge out of a whole circle. So here you can imagine that being the full circle, but here we're only considering a single sector, a single wedge. And in trigonometry, you learn that the area of a sector is 1/2 times r squared times theta, where theta is the angle, the central angle here, over which the sector is measured, and r is the distance from the center to the outside. So here this would be r, and this would be theta. The important thing here is theta should be in radians, not in degrees. Right? So here this make sure that's in radians. But otherwise this works out rather nicely. All right. So this might be something you haven't seen in a while, but that's the formula for the area of a sector. Now, whenever you have a sector that is not going all the way back to the origin, we could do the following. We could say, okay, look, let's say I only had this sector. You say, well, that's not really a sector anymore, is it? That's some other shape. Well, no, it's not. But notice, if I take this smaller sector in here, if I subtract that away, that leaves me just that little piece up there. So this area, so this is for a sector. This area is given by, well, let's see, you have a big sector. So I'm going to say that's R1 squared theta. And then here I have a much smaller sector. Well, it's got the same theta. So really it's just going to be R2 squared of theta. Just like that. All right, well now I have a common factor of 1/2 and theta. So here this area right here would be given by 1/2 times R1 squared minus R2 squared times theta. Okay, nice. So what? Well, remember that in polar coordinates, that's how you measure position, r and theta, a distance away from some pole and an angle that measures the amount that this opens up. Okay, so what? Well, if I'm trying to find something in 3D, I note that just like my integrals over the rectangular coordinate system, here I could still have some region. And if that region is not something that I want to describe in rectangular coordinates, I could describe it in polar coordinates. I could still have a region R. And over that region R, I could still have some object. I could still say, okay, here's some object that exists over that. And I could still ask for the volume beneath that surface down to that axis. So here we should still be able to do the same thing. And as we saw in the previous sections, in order to do that, we're going to approximate it using these little tiny patches along the domain. But now in rectangular coordinates, the patches, it was natural to have them be little rectangles, hence rectangular coordinates. Here, these aren't exactly rectangles, but they serve their purpose. I could break this domain up into a bunch of these little patches that are shaped almost like a rectangle, but not quite. And this here will show us how to do that. So consider now that you have one of these little tiny patches. All right, well, let's see. I have, this is going all the way back to my pole, but I don't want to consider it going all the way back to my pole. I want to consider just a little tiny patch. Right? Now here, you're imagining that this is a small little sweep across the angle theta. Here, I'm looking at this is one of these little patches. So it's not even the entire region. It's just that little tiny sliver. So here, this theta, it's a really small theta. So here I'm going to say delta theta. A little tiny change in the angle from this line to this line. A little tiny change in my angle from this line to this line. Okay, cool. So now what? Well, I notice that I have two radii. I think radii. Here, I'll call this one, from here to here, I'll call this R1. And from here to here, I'll call this one R2. So R1 is the smaller one, R2 is the larger one. Oh, you know what? Over here I said R1 is the larger one and R2 is the smaller. So let me keep with that. All right. So now I have a larger radius R1 and a smaller radius R2. So I can do this over here. I could say, okay, well then this area right here is equal to, and notice this is not an approximation. This is actually equal. This is equal to 1/2 times R sub 1 squared minus R sub 2 squared times, well, now my theta is a little tiny theta, so I'm saying delta theta. Well, you know what? That little area is a really tiny little area. So we're going to say delta A, like that, right? A small change in our area from one place to another. A small change in our angle from one place to another. All right, so now what? Well, we can simplify this just a little bit. Notice I can write this as 1/2. I'm going to do something that I don't usually do when I'm doing this in trigonometry, but here I'm going to go ahead and factor this. After all, this is the difference of squares. I can write this as R1 squared plus R2 squared and R1 squared minus R2 squared, delta theta. But now notice that's a little tiny change in R. That's the distance from R1 to R2. Well, that's a little tiny change in the direction of R. Let's call that delta R. Okay, so I can write this as delta R, and that's delta theta. Now keep in mind, there's going to be different versions of this, because after all, here I'm describing this one little patch, but I could describe a different one. So here, maybe I should say that's Ri and theta I, like this, yeah? Because here I'm describing that one in particular, but of course there are others. Well, now that's an average. R1 and R2, oh, my apologies. I factored this out. There should be no more squares anymore, right? Yeah. There we go. Here, R1 and R2, if I add them together and I divide by 2, that's an average. That's how you compute averages. So what this part right here is it's the average distance from the pole between here and here. So this gives me the spot right in the middle of that little patch. So here I'm going to call this a single point. I'm going to call this R. All right? So this will be R, and R will represent the average between R1 and R2. Okay, so here, that is the area of that little tiny patch right there. And here, note this is the average of R1 and R2. Okay, so now what? Well, now we've described the little patches on the domain, but what about this upper surface? And you say, well, it's given by a function. It's given by f. Now, f of what? Usually we deal with f of x and y, but there's no x and y here. Oh, okay, well then I have to convert to polar coordinates. Well, yeah, but there's a fixed way of doing that. Recall, again, we're back in trigonometry, that the conversion between polar and rectangular, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now again, keep in mind there are different x's and y's here. So here that's going to be r I and theta I. We're going to go ahead and write all of those as I. Oh, and I should do the same thing for here. Okay, so now what? Well, now I can put this together. Because after all, I know that to describe this solid, I'm using a double integral. I'm using a double integral over a region of f of x comma y dA. And you say, whoa, hold on. You said that wasn't x and y. You said it was r and theta. Well, yeah, that's true. This is what we know to be generally true. A volume of a solid is given by a double integral. But now, since we're dealing with things in polar coordinates, we're going to have to replace some of these things. We're still taking a double integral over that same region, but now, instead of f of x and y, x is no longer x. X is I cosine theta, and y is r sine of theta. Oh, actually, you know what? I may be jumping the gun here just a little bit. I'm saying something which is true, but we haven't really gotten there yet, have we? Because what we can say is, well, I can approximate these things. I can approximate the volume of this solid is approximately equal to, well, let's see. This will just give me the area of a little patch times the height. Oh, well, the height is just given by my function. I'll call this function up here f. And f could be used, it can be written in terms of x and y, or it can be written in terms of r and theta. So here I can write this as f of, and instead of x and y, let me use r and theta. That's ri cosine of theta I. And then ri sine of theta I. So that's your height times your base. Well, yeah, but the area of our base is this thing that we saw over here. That's going to be our r delta ri delta theta I. Just like that. Well, yeah, but that's just the volume of one of these little things. I took one of these little patches and I found a little solid region, a little solid object, and found its volume. All I've done is I found the volume of this one. I have a bunch of other ones that I need to find the volume of. Okay, well, find all of them and then add them together. We're going to take the sum as I goes from 1 up to n. So if you found 50 of these, well, we add up all 50 and that gives you your volume. But now, that's an approximation. We can make that approximation better by taking this and shrinking it down. Just like we did when we were looking at iterated integrals in terms of x and y. Here, we consider the norm of our partition to be the diagonal distance across here. So when we write that the norm of our partition approaches 0, what that means is that these opposite corners are coming together. But if the opposite corners are coming together, that means that theta is getting smaller, the delta theta, and these R2 and R1 are moving closer together. So here, instead of saying that's approximately equal to, that is now the limit as n approaches infinity. That's the same as saying the norm of our partition approaches 0. Remember, the norm of the partition just means the distance across one of these. They're all different sizes, so when we say the norm of the partition approaches 0, that means that even the biggest one approaches 0. So here, limit as n approaches 0, or norm of our partition approaches, n approaches infinity, norm approaches 0, of the sum as I goes from 1 to n, of f of ri cosine of theta I, comma ri sine of theta I, r of I delta r of I delta theta I. But that's an integral. After all, that's the limit of a sum. Here we have the limit of a, well, these are just heights times bases. This is an integral. Well, yeah, but it's an integral over two different variables, r and theta. Okay, so it's a double integral. So here, this is the double integral of, well, let's see, our function is no longer a function of x and y. Now it's a function of r cosine of theta and r sine of theta. Here, this is just r. This is just a little tag along, right? It just sort of shows up right here because of that term. That's not a differential. It's just r. It's just a number, right? Or I suppose it's just a variable here. And here, that's delta r, well, that's as you pass through the limit, that becomes your differential dr, and same thing, that's d theta, just like this. This thing right here, I'm going to give it a name, which for now doesn't really make any sense, but in a later section we'll talk more about it. This is called the Jacobian. The Jacobian is something that allows you to transform from one variable to another. For now, it's just a name. I'll refer to it, oh, this is the Jacobian for polar coordinates, but really it's just the variable r. But of course, this is a iterated integral. Notice we're integrating with respect to r, then with respect to theta. But of course, that's describing a solid region, which in a previous section we saw was just a double integral over r. So here, that suggests that the double integral over r of f of x comma y dA, which we saw in a previous section, which would have given us this region, the volume of this region, is equal to the iterated integral, again over the region r, of f r cosine of theta, comma r sine of theta, times r dr d theta. That brings us to our theorem, the main theorem of this section. And that just formally states what we develop here. All right? So our theorem states, so this is the theorem for changing variables to polar. Let R be a plane region made up of all points x comma y. Okay, so you have a region in the plane, such that x and y can be expressed as r cosine of theta and r sine of theta respectively, where you satisfy the following conditions. These points satisfy the following conditions. Your r is bound somewhere between two functions of theta. That lowest function of theta must be positive, which means certainly that one would be positive as well. And here, r is bound by functions of theta. Here, theta is just bound by two constants. Here we use alpha and beta. And there's one more restriction. The difference between, if you have beta minus alpha, that's got to be between 0 and 2 pi. So no fair wrapping all the way around the circle multiple times. Right? And no fair having negative angles. Everything should go, if you take b minus a, it should be some angle that's between 0 and 2 pi. All right? So if, and we have one more set of conditions. Let G1 and G2 be continuous on alpha and beta. So here, these two functions that bound our r, they're continuous on the interval from alpha to beta. And let f be a function that's continuous over all of this, over a region r. Drawing that out, we get the same illustration that we saw before. Here I have a region in the plane. I'll call that r. It can be expressed in polar coordinates, right? X is equal to r cosine theta, r sine of theta. Technically, anything can be expressed in polar coordinates, any region. It's just many of them are not convenient to do so. Here, we want something that is conveniently done this way. In any event, these satisfy the condition that r is bound somewhere between theta 1 and g of theta 1 and g of theta 2. And here we have some outer curve which bounds our radius. It doesn't go out forever. It stops at some curve. Here, this wouldn't have to be a nice smooth curve. It could be something a little less nice. Right? And here we have another lower function which bounds the minimum value of r. Notice that must be positive. Or in other words, it can go all the way back to the origin, but no further back. No for having negative radii. It doesn't have to go back to the origin, though. Notice it's greater than or equal to 0. So if we wanted, we could even have something that looks like this. It wouldn't have to go all the way back to the origin. Okay, so here's a region. This would be my G1. This would be my G2. Notice that my thetas are bound by constants. I have an angle theta here, and I have an angle theta here. Here, that's the smallest angle of theta. Right here, it's closest to the x-axis. It's closest to 0. So that would be alpha. And over here, this angle would be given by beta. So I have some region that can be described in polar coordinates Here, the distance away from the pole can be whatever, as long as it's a function, as long as it's continuous. But the angles must be bounded by some constants. All right? And finally, here we have some function that is continuous over this region R. Well, obviously, if it's a function that's continuous over a region, that must be a surface up here in the x, y, z coordinate system. So it would be something up here. Something like this. All right, so we have some object like that. All right, so if all of that's true, if you're in that situation, then you can compute the double integral of f over a. In other words, you can find the volume of this by the double integral. This is now f of r cosine theta, r sine of theta. Here there's the Jacobians, an extra factor of r. You would first integrate with respect to r. So here that would be a function of theta. But then you would integrate at the end with respect to theta, which are just a couple of constants, alpha and beta. Right? And this just formalizes what we sketched out on the previous page. So let's take an example now. Let's go ahead and let's start up here. We're going to go ahead and integrate. Oh, let's go ahead and try this. The integral from 0 to 4 of the integral from 0 to the square root of 4y minus y squared x squared dx dy. And if you remember our last section, this might start bringing back some terrible flashbacks. We start seeing here radicals, and we start remembering things about trig substitutions and integration by parts and geometric arguments, and that could be very, very complicated. Well, here, we're not going to do it this way. We're going to do this by converting to polar coordinates. The first thing that we want to do is we want to describe this region in a different way. A good way to do this is to try to figure out what this object is. This is a planar region, right? If I ignore this, this right here is just a region on the plane. So let's go ahead and draw that out. Here, let's see. This is telling me that I am bounded by x is equal to 0 and x is equal to that thing. Oh, well, I know what x equals to 0 looks like. That's the y-axis. What's that thing? Well, let's see. Let me go ahead and do some work over here on the side. If I take x is equal to 4y minus y, and all that's under a square root, personally, I just don't know what that graph looks like. Oh, but well, maybe I can make things a little easier on myself if I square both sides. After all, that square root's kind of in my way. Okay. All right, well now, that looks a little more familiar. Let me move all these over here. Let me write this as x squared plus y squared minus 4y equals to 0. Oh, but I can complete the square. Hey, look, if I take that number, cut it in half, and square it, that gives me a plus 4 there and a plus 4 there. I'm completing the square. But now, I can write this as x squared times this part right here, plus. This part right here factors down to be y minus 2 quantity squared, and 0 plus 4 is 4. Oh, but I recognize this. This is the equation of a circle. This is a circle that is centered at 0, comma 2, and that has a radius of 2. Okay, so I should be able to draw that out. Here I want a center of 0, comma 2. Okay, so there we go. Let's call that 0, 2. And now I have a radius of 2. So that's going to go down 2 steps, up 2 steps, left and right. Oh, okay, so now I want something that's bound by, oh, let's see here. I want my x to be 0. That's my y-axis. Okay, and then I want it to be above the y-axis but below this curve. Oh, well, that's all of this. Here, that's going to be what? Positive 2, that'll be negative 2, that'll be positive 4 up here. So here, we want everything from here up to here, and then my y values, I want, no, I'm sorry. That's backwards. I want x to equal to 0. That's the y-axis. So x equals to 0 is the y-axis, and so I want things that are between the y-axis and this curve. You say, well, what do you mean between? Which way do I go? Well, going back to your original expression here, this is the positive square root. Now, the positive square root gives you positive values. So this is the region that I want. Here, this is x equals to 0. Here, this is x equals to the square root of 4y minus y squared. And I want all the stuff in between those two. The least is 0. The most is that curve. Now my y values, I want this to go from 0 to 4. Okay, well down here is y equals to 0, and up here is y equals to 4. So that means we don't want to cut this off. We don't want like part of this. We want the whole thing. Okay, so there's my region R. What I need to do now is I need to express that region R, instead of writing it in rectangular, I need to write this in polar coordinates. Okay, well, thinking back, I remember that I can express a circle in polar coordinates. If the center of the circle is on one of my axes, that's pretty simple. Because if it's on the x-axis, then my equation simply reads r equals to some number times the cosine of theta. If it's on the y-axis, well then my equation would read r equals to some number times the sine of theta. Okay? So, because that center rests on my y-axis, then r equals something times the sine of theta. That something is simply going to be the point that's furthest away from the pole. So here, that point furthest away is the number 4. So I can express this entire circle as r equals to 4 sine of theta. Okay, but now I don't want the entire circle. I only want half of it. Well, that's where my angle is going to come in. Because here, I notice that I can express all of this stuff right here as starting from the origin, going out to this curve. Starting from the origin, going out to this curve. So I know that my r is going to start at the origin. Okay, so r has got to be between 0 and the maximum it ever gets to is this curve, 4 sine of theta. But now, if I keep going, if I start at the angle 0 and I keep going to angle pi over 3, pi over 4, I'm saying this backwards, pi over 6, pi over 4, pi over 3, if I get to pi over 2, that's going from the origin straight up. Oh, but that's it. I shouldn't keep going any further. So here, this is covered by keeping my theta from 0 to pi over 6, pi over 4, pi over 3, pi over 2 is the biggest. So theta is between 0 and pi over 2. If you're having a hard time remembering some of these formulas, go back to chapter 10 in your text. In particular, section 10.4 will have all of the stuff you need for here. All right, so we have our boundaries. Okay, so let's see here. I'm going to change this into polar coordinates. So now this is the integral. I have my theta is bounded by constants, which is good. That's what I want. That's from 0 to pi over 2. Here, that's my boundary of r. Well, that's bounded by functions of theta. So that's good. That's 0 and 4 sine of theta, just like that. Here, this x squared, remember, it's not going to stay x squared. All x's become r cosine of theta. All y's become r sine of theta. So this x squared is now going to become r cosine of theta, quantity squared. And then your dA, which before, with Fubini's theorem, became dx dy, now is r dr d theta. You're going to have an extra factor of r right here. R dr d theta. Sometimes that r will just be another term, another factor rather. Sometimes it'll just be another factor. Other times, it'll be the most important thing. It'll be, hey, if it wasn't for this, the rest of the problem would just be stuck. but it will always make a difference. So make sure you put the Jacobian in here. Make sure you put in that extra factor of r. And there we go. We've converted into r. This bit of a geometric interpretation of this region allows us to change our boundaries rather nicely. And now this can be integrated significantly more simply than having to go through the trig substitution that we otherwise might have had to do. Here, let's write this as, let's see here. That's r squared times another r. Well, that's r to the third. Cosine squared of theta dr d theta. I squared my cosine. I squared my r, but then there's another r out here, which joins in. And now we're ready to go. If we integrate with respect to r, that's a constant, so we're not going to worry about that. That's going to be the integral from 0 to pi over 2 of, okay, well, with respect to r, that's a constant. I don't even need to worry about that. Just this part right here. R to the 4th over 4 times your constant. R to the 4th over 4 times our constant. And that's going to be from 0, let's see, r equals to 0, I should label that, up to r equals 4 sine of theta, like that. Those are our upper and our lower bounds. Okay, so now we can go ahead and substitute these in. If I plug in 0, I guess I should write my d theta here. All right, so if I plug in 0, well, that whole thing is 0, so we don't worry about that, right? 0 times anything is 0. If I plug in 4 sine of theta, that's going to give me the integral from 0 to pi over 2 of, let's see, that's going to be 4 sine of theta to the 4th power, and that's all over 4, times the cosine squared of theta, d theta. Let's see, 4 to the 4th divided by 4 is 4 to the 3rd, and 4 to the 3rd is 64. So we can factor that out, and that'll be 64 times the integral from 0 to pi over 2 of sine to the 4th of theta times cosine squared of theta d theta. Right, just like that. Now, at first glance, this one looks pretty bad because you say, okay, well, now I have even powers of sine and cosine, so I have to use the power reduction formulas. And when I use the power reduction formulas, it's going to expand out very, very big. And of course, we can do that. We can always write this out as sine squared of theta times sine squared of theta. And then we could use the power reduction formula for sine, power reduction formula for sine again, and the power reduction formula for cosine. But then we'd have to multiply that out and do it again and again and again. Because notice, this is a 6th degree, not polynomial. This is the 6th degree integrand. Well, yeah, which means the power reduction formula isn't going to get you to where you need to go right away. So there's a whole lot of algebra that's required, a whole lot of trigonometry that's required to expand this out, which is fine. But there's another formula specifically for this. Now, this is a lesser known formula. It is something that we see in Cal 2, but it might be something you don't remember very well. This is called Wallace's formula. Oh, Wallace's. I might spell this wrong. I believe it's Wallace's formula like this with an I. And Wallace's formula states that, well, there's two cases. If n is odd, then the integral from 0 to pi over 2 of sine of x to the power n dx is given by 2/3 times 4/5 times 6/7. Notice the pattern. It's just 2, 3, 4, 5, 6, 7 like that. Times dot dot dot, and I guess I don't have to continue down here. Times n minus 1 over n, just like that. On the other hand, if n is even, then the integral from 0 to pi over 2 of the sine to the power n of x dx is given by, that would be 1/2, and then that would be 3/4 and then 5/6, and then 7/8, and so forth and so on, all the way until you get to, it's going to be the same one here, n minus 1 over n, but then that's going to be multiplied by pi over 2. Over 2, like that. All right. Well, the one where it's odd is not very interesting to us, because if you did have an odd power here, that would be very simple to integrate. You take off the single odd power, treat that as your differential, and integrate. That would be done very quickly. Here, this one is the one of interest to us. So let's go ahead and keep that. Oh, let's go ahead and put this over here. Let's go ahead and keep that going. I want to find 64, and I'm just writing down where I was. 64 times the integral from 0 to pi over 2 of sine to the 4th power of theta times cosine squared of theta d theta. And of course here I can write cosine squared of theta as 1 minus sine squared of theta. So that's 0 to pi over 2. That's going to be sine squared, sine to the 4th of theta times 1 minus sine squared of theta. Looks just like that. And now I can distribute that, and that'll give me 64 times the integral from 0 to pi over 2 of sine to the 4th of theta minus sine to the 6th of theta d theta. But now I can separate that. That's 64 times the integral from 0 to pi over 2 of sine to the 4th of theta, which, because it's an even power of sine, integrated from 0 to pi over 2, and it has to be those specific boundaries, we can use Wallace's formula. Likewise, here, that's also the integral from 0 to pi over 2, and that is also an even power of sine. So now we can use Wallace's formula, and that's 64 times, and now let me do each of these on its own. Here, this integral, using Wallace's formula, that's going to be, all right, we have an even power. So here we're just going to start counting up until we get to a denominator that matches the power on your sign. In this case, it doesn't take very long. We're going to get up to power 4. So 1, 2, 3, 4. So it's going to be 1/2 times 3/4, and that's it. We've gotten to the power. All right, power 4. We stop at when our denominator is at that same power. We stop when our denominator is at that same power. And now the whole thing is multiplied by pi over 2. Like that. Minus, and I do the same thing over here, except now it's to the power 6. Okay, so I'm going to keep going until this denominator matches that power. Okay, so it's going to be 1 over 2 times 3 over 4 times 5 over 6. And now I'm done because that's reached power 6. And again, that gets multiplied by pi over 2. Just like that. So putting this together, that's going to give us 64 times, that's going to be 3 pi over 16 minus, that's going to be 15 pi over, I was trying to fit that on one line, but over, let's see, that's going to be 8 times 6 is 48 times 2 is 90, what did I say? 96, just like that. And now that simplifies out just a bit. Let's see, that's 64 times, let's see, that's 3 pi over 16 minus, we can divide top and bottom here by 3, yeah, by 3. That'll give us 5 pi over 32. I can now multiply this top and bottom by 2 to give me a common denominator. So that'll give me 6 pi minus 5 pi. Well, that'll just be 1 pi over, the common denominator is 32. And now these divide away, and maybe just a bit not counterintuitive, a bit anticlimactic, we end up with 2 pi. And there we go. Now this was a use of Wallace's formula as a bit of a labor-saving device. We started here, we changed to polar, and then we performed our integration. From polar, that was our first integration. Our second integration looks like it would have been a little longer, but using Wallace's formula, we can take our second integration, split it apart, and then integrate each one. If you didn't remember Wallace's formula, that's fine. You would use the power reduction formulas on these, like we did on an example in a previous section. It is a little longer. It's still manageable, but this is certainly quite a bit nicer. All right, now let's take a look at another example here. We're going to find the volume of the solid. We're going to find the volume of the solid inside of the hemisphere and outside of the cylinder. All right, so let's go ahead and give a quick illustration of this. All right, let's see here. So this is a hemisphere. Z equals the square root of 16 minus x squared minus y squared. All right, let's see. Z equals 16 minus x squared minus y squared under a square root. If I square both sides, that's going to be z squared equals 16 minus x squared minus y squared. And if I move these all over here, that'll give me x squared plus y squared plus z squared equals to 16. Notice that if I take the different traces, that's a circle of radius 4. If I take this trace, that's a circle in the xz plane of radius 4. And if I take that trace, that's a circle of radius 4 in the yz plane. So no matter what trace I take, I end up with a circle of radius 4. Oh, that must mean it's a sphere. Every direction you look, it's a circle. So it's a sphere. But notice that z was positive. Here, this is positive. You say, well, how do you know that? Well, because it's the positive square root. So because that's positive, that means I want the sphere, but I only want the part where z is positive. So that's going to be a circle of radius 4 on the xy plane, but only the upper half of the circles on the on the xz plane and on the yz plane. So here I have a hemisphere, the upper half of that sphere. Okay, so now the other thing that I want is here, let's go ahead and draw this out in color. The other thing that I want is I want a cylinder. Now cylinders are nice because you just draw their generating curve and then from there you just go along the missing variable's direction. Here, x squared plus y squared equals to 1. Well, that's a circle of radius 1. That's centered at the origin. Okay, so I have a circle of radius 1. That's well inside of this sphere. And that'll be 1 and 1. And that's flat. That's on the xy plane. But now notice z is the missing variable, which means z is a free variable. It's allowed to do whatever you like. So z can go up as high or as low as you like. So this will go up and down forever. Now, of course, the down part doesn't really matter because we're looking at the stuff that's inside of the hemisphere. So it really should be the stuff that's above the axis. Here, the cylinder goes on forever in both directions, but we're not going to really care about both directions. Just like that. So now what we want is we want all the stuff that's inside of this blue hemisphere and outside of the cylinder. In other words, in between those two skins. All right? So, well, let's take a look at our region. Look on the xy plane. This is all the stuff that's outside of this circle of radius 1 and that is inside a circle of radius 4. It's outside of the cylinder and inside of the sphere. So here, let me just look at the region. If I look at just my region R, it's reasonably simple. It's just an annulus, a washer, a ring, a circle, or rather a disk with a smaller disk punched out. All right, here that's 4, 4, minus 4, and minus 4. That's 1, 1, minus 1, and minus 1. And here, that's the region on the xy plane. Well, that's going to be very easy to describe in polar coordinates. Okay, so let me describe that in polar coordinates. I need to describe r and theta. Here, my r, well, notice, I don't want to go all the way to the pole. I want to have the closest I get to the pole to be 1 unit away. I want the furthest I get to the pole to be 4 units away, and all the stuff in between. Okay, so I want r to be greater than or equal to 1, right? That's the smallest it should get, and less than or equal to 4. That's the largest it should get. Now, if r is equal to 1, that puts me right there. If r is equal to 4, that puts me out here. And what I really want is all the stuff in between. Well, yeah, but that's only this part. How do I go all the way around? Well, that's my angle. I want to go all the way around so that I'm covering not just this little strip between 1 and 4, but every part of this all the way around until I come back and reach my starting point. Oh, well, that's just from 0 all the way out to 2 pi. So your theta is going to go from 0 to 2 pi. Remember when we define this stuff, we say that these should not be negative. This angle theta should not be negative. And the distance between these should not be more than 2 pi. Beta minus alpha should be less than or equal to 2 pi, which here, that's about as far as you could get it. All right. So this describes our region. We like this kind of description. We like constant boundaries because constant boundaries make for easy integrations. So now we take this and say, okay, we want to find all of the stuff that's in between the two surfaces. So now we're ready to set things up. We can say, okay, we want to find this volume in here. We want to find all the stuff that's inside of the sphere but outside of this cylinder. Well, okay, but notice that as long as I'm outside of the cylinder, the only function that I need to worry about is the function that gives me the hemisphere. After all, every height, the distance from this region up to the top surface, is from the xy plane up to this blue hemisphere. Here, we don't need to worry about this because here, this part has been punched out already. This is gone. There's a big empty gap here. So, the height of each of these little rectangles that would be, or these little solids, these little, what would we call them? These little, not quite parallelopipeds because they're not quite rectangular, but just these 3D little slightly warped boxes, little 3D shapes. These would only be defined as the distance from the xy plane up to the blue hemisphere. Okay, well then that's just being defined by this. I have the distance from here to here as being defined by z equals to the square root of 16 minus x squared minus y squared. Well, yeah, but I'm supposed to be doing things in polar coordinates. Oh, well, that's fine. Because here, x squared and y squared, hey, I know that r cosine of theta is equal to x. I know y is equal to r sine of theta. So if I take x squared minus y, x squared plus y squared, then that's going to be r squared cosine squared of theta plus r squared sine squared of theta. I can factor out r squared of theta here, or I can factor out r squared, giving me cosine squared of theta plus sine squared of theta, just like that. And now that, by the Pythagorean identity, just the number 1. So that's just r squared. All right, cool. So here, x squared plus y squared is equal to r squared, which means minus x squared minus y squared, which is really the negative of x squared plus y squared. That's equal to negative r squared. Okay, so right here, instead of writing this as 16 minus x squared minus y squared, I could just write that as the square root of 16 minus r squared. 16, and that becomes minus r squared. All right, so now we're ready to go. We can set this up and say the volume is just going to be the integral over this region, over this annulus, over this washer, this disc with a little disc punched out, from the axis, from the xy plane up to this hemisphere. All right, well, we now know how to describe all of those things. I'm going to want my volume to equal to the double integral over r of f of x comma y dA, which, given our change of variables theorem, can now be written as follows. We want to write f of x comma y in terms of polar coordinates. Well, we did that. Instead of writing it as 16 minus x squared minus y squared under a square root, we can just write it as square root of 16 minus r squared under a square root. We need to be able to describe our region in polar coordinates. Well, yeah, but we've done that. Right? We want to do this dr d theta, so make sure you put these in the right order. Here we're going to say that dr goes here. So that's going to be, r is bound between 1 and 4. That's going to be your first integral. And then the second integral that you're going to take is going to be with respect to theta. And theta is from 0 to 2 pi. Now, if you look at this, you might think, oh, God, that's not very good, is it? Look, I've got the difference of squares inside of a square root. That's more of that. Substitution, the trig substitution stuff, right? Wallace formula is not going to save me here because this is not from 0 to pi over 2 or anything of that nature. Well, that would normally be the case. This is a terribly long integral to have to take anytime you see something like this. But we're missing one thing. Because remember, when you convert from rectangular to polar, you have this extra factor of r. You have your Jacobian. And while sometimes it's just, it's there, we're going to use it, and it'll be part of the problem. Other times, that extra Jacobian, that extra r, that gets multiplied along with f of r sine theta cosine theta, is what's necessary to make this problem much, much simpler. Incidentally, if you try to do this problem with rectangular coordinates, you will get the same answer that we're about to get. It's going to be much more complicated and a lot less pleasant. So here, pause the video for a moment and give this one a try. As it's currently written, go ahead and integrate, and once you get an answer, unpause and we'll go through it together. All right, so let's give this a try. Let me rewrite this over here. So we can use a substitution now. That extra r will serve as the differential. Note here, I can take u is equal to 16 minus r squared. So du is equal to minus 2r dr. And here I have an r dr. Okay, let's get rid of that negative 2. So negative 1/2 du is equal to r dr. This is one of the main attractions to using polar coordinates. In some cases, this r is just there. But in some cases, it'll be what's necessary to turn problems from very long, complicated problems to something much shorter and simpler. We will change to other types of variables in later sections for the exact same reason. So now, let's look at this and integrate. We can write this expression as, let's go ahead and write those integrals that were out here, 0 to 2 pi d theta, like that. So now I'm looking at the stuff in here, and I can convert that now into a completely different expression. I can write this now as the integral of, let's see, that's u, so I can write it as the square root of u. R dr, well, that's 1/2 du. So let me put the 1/2 in the front. Oh, that should be a minus 1/2. So that's minus 1/2 square root of u du. Maybe space that out just a bit. That'll be minus 1/2 square root of u du. All right, and here, let me go ahead and change my boundaries as well. After all, if this is what r is equal to right now, if r is equal to 1, that means u is equal to 16 minus 1 squared. Or in other words, it's equal to 15. So here, this lower bound can be written as 15 in the upper bound. In the new variable. The upper bound, I can do something similar. I can write this as u by saying, well, if r is equal to 4, that's u equals to 16 minus 4 squared, which is 0. So that's my new upper bound. Yeah, that looks backwards from usual, but that is what they are. These converted directly into these. So now this is something we can integrate and just plug in the numbers directly. All right, so that's going to be the antiderivative of the square root of u is going to be, well, let's leave our 1/2 there. That's u to the 3/2 power times 2/3, like that. And we're going to evaluate that from 15 up to 0. We still haven't evaluated this outer integral, like that. Here, that simplifies quite a bit. And now we can write this as negative 1/3. These 2's are gone, negative 1/3. I can plug in 0 here. Well, here, let's just write this way for now. If I plug in 0, well, that's going to make the whole thing 0. Minus, well, now if I plug in 15, I get minus 1/3 times 15 to the 3/2. Well, that's going to be 0, so that'll just go away. That's 0. Here, double negative becomes a positive, so that does work out eventually here. That negative and that flipping around, they both go away. So here, this will give me, that's now a positive. Let's see, 15 to the 3/2. That's the same as 15 times the square root of 15. So if I take that 15 and divide it by 3, I get 5, and then the square root of 15 stays put. So there we go. That's a constant. Just like that. But now, if I'm taking the integral of a constant, well, that's just that constant times the variable, times theta. So here I can write this as 5 square root of 15 times theta, and that's being evaluated from wherever theta is equal to 0 up to whenever theta is equal to 2 pi. If I plug in 2 pi right here, I get that's 10 pi root 15. Oops, 10 pi root 15. Minus, if I plug in 0 right here, well, I'm going to get 0. So in the end, I get 10 pi root 15. And that makes us happy. Finally, as our last problem, we can see something that we saw in a previous section, and that is that you can use a double integral, you can use an iterated integral to find the area of a region. That is done by simply taking the double integral of just the differential of a. So recall that the area of a region R can be found by taking the double integral over the region R dA. That makes sense. Basically, you're saying, okay, take the little pieces of area and add them up in every direction, and that'll give you your total area. We saw it typically written this way. We saw it written as the region, the iterated integral over the region R, dx dy, or dy dx. We saw that by Fubini's theorem. And we saw that they could be converted one way or the other. Well, we could also do this with polar coordinates, because after all, this is still the same region, but instead of describing it in terms of x or y, we can describe it in terms of r and theta. So here, instead of dx dy, we would do dr d theta. But don't forget, there's that extra factor of r that occurs whenever you change from rectangular to polar, your Jacobian. Like I said, for now, that name doesn't really mean anything other than it's a label. We'll talk more about that in later sections. But don't forget, when you convert from rectangular to polar, this extra factor of r just sort of shows up. So here, let's take a look at a very simple example of this. And, well, frankly, there's not really any complicated examples of this, at least not for now. So let's go ahead and take the last example for the section. Let's go ahead and find the area of the region. And here they give it to us as an illustration. They draw it for us. They've drawn for us an annulus. It's got a inner radius of 2 and it's got an outer radius of 4. Okay, and we want to find the area in here. Well, what we want to do is we want to describe this region in polar coordinates. Well, we saw the description of an annulus just a moment ago. Here, this R is bound. The smallest it ever gets is 2. The largest it ever gets is 4. So R is bound between 2 and 4. Now, that would only cover this strip. But if we make our theta go up to 2 pi, up to pi, 3 pi over 2, and wrap around back to 2 pi, then that would cover the entire region. So here theta goes from 0 up to 2 pi. All right, so here the area is equal to the double integral over R dA, which is going to be written as the double integral. Here we can write this as, instead of dA, we can write this as R dr d theta. Here, our R is bound between 2 and 4, and our theta is bound between 0 and 2 pi. Just like that. If we take the antiderivative of R with respect to R, that's going to give us, we haven't done the integral from 0 to 2 pi yet. We're just doing this one first. That's going to give us R squared over 2, evaluated from 2 up to 4. Just like that. But now we can go ahead and take that and simplify. This is now the integral from 0 to 2 pi of, you can pop in this 4 right here, and pop in this 2 right here. 4 squared is 16. Well, here, let's just do the arithmetic here. 4 squared is 16, divided by 2 is 8, minus 2 squared is 4, divided by 2 is 2. So that's just going to give us 6. All right, so that's going to give us the integral from 0 to 2 pi of the number 6 d theta. Oh, okay, but now we can take the integral from 0 to 2 pi of a constant with respect to theta. Well, that'll just give us 6 theta, integral from 0 to 2 pi. Just like that. All of our expressions for now are nice and straightforward. In later sections, we'll start seeing some that are just a little bit more involved, but really not that much more. So here, we can evaluate at 2 pi, 6 times 2 pi. We can evaluate at 0, 6 times 0. And when we subtract, we get our result. The area of this region is given by 12 pi square units. Notice this is an area, whereas the previous one was a volume. The main difference there is here, we're simply integrating the area. We're adding up all the area that we have. Whereas in our previous example, we were looking for a volume because we were adding up these, oh, where were they? We were adding up these z values over a region. Right? Here we have a third dimension. Over here, we're just adding up things along the region. Right? So that's the end of our section. And for your exercises, go ahead and try the following. For section 14.3, go ahead and try 9 through 49. Let's do every other odd. So that's the end of our section, and I hope you all have a nice day.